Very good morning to folks from China and good evening to folks from the US. This is Rajarajan Sivaraj. I'm a principal technical architect with Mavenir. And I'm here to talk about unraveling the mysteries of cellular RAN through OpenRAN architecture and programmable intelligence. I would also like to acknowledge Peter McKinnon and Kuntal from Mavenir for giving me some inputs to the slide deck. So what is the context of this talk? So in this forum, we saw a bunch of speakers focus on OpenRAN, focus on the OpenRAN architecture, and what kind of machine learning lifecycle, what kind of machine learning analytics you can actually use, service level agreements that you can use in OpenRAN. But what I am trying to focus here in this talk is, what are the mysteries of cellular RAN? Like getting into the motivation of OpenRAN, why we actually need OpenRAN, because there are certain mysteries in cellular RAN. There is a lot of black box in cellular RAN and legacy systems. So we want to unravel that black box, and we basically want to unravel those mysteries and solve those mysteries using OpenRAN architecture. OpenRAN architecture is the best means to solve these mysteries. And the reason why we need to unravel these mysteries is because we want to make the cellular RAN more optimal and more customized. So that's going to be the context of my talk. So a quick introduction. So I want to get started with the functions of the RAN protocol stack. So there are three kinds of functions in the RAN protocol stack. One is control plane that deals with connectivity, mobility, user context, and bearer context for traffic flows, and signaling operations related to all these connectivity, mobility, user context, bearer context, etc. between the radio access network and the user equipment. So that's the control plane. The user plane is predominantly responsible for transmission of data, uplink, downlink, sidelink between the RAN and the user equipment. And management plane is mainly responsible for network element configuration of the RAN. Now, there are layers of the RAN protocol stack, which you'll be able to see in a bit. And these layers manage these functions using procedures and by maintaining relevant user state information. Nevertheless, the interdependencies between the layers of the RAN protocol stack are quite complex, and some network and traffic dynamics impacts the procedures and impacts the performance of these functions. So a quick intro on the RAN functions and procedures. So basically, excuse me. So procedures are managed by vendor proprietary algorithms in legacy cellular RAN systems. Now, these vendor proprietary algorithms are not necessarily optimal, nor data-driven, nor programmable. And it is quite challenging to characterize these algorithms and their performance because of vendor-specific, vendor proprietary implementation. And it is also difficult to quantify the intricate interdependencies between the entities and between the layers of the RAN protocol stack, because most of these are implemented as a black box. But optimization of these procedures that the RAN protocol stack handles requires unraveling this RAN black box, requires unraveling this vendor proprietary implementation of the RAN, compute and predict performance of the algorithms using analytics and machine learning and artificial intelligence. And these will basically help optimize the functions of the RAN protocol stack. And principles of software-defined networking and open interfaces aid in unraveling this RAN black box and controlling the optimization of the procedures, especially if any third-party applications want to optimize the procedures that are implemented by the vendor, or even if the operator wants to optimize the procedures implemented by the vendor. The means of doing this is by unraveling this RAN black box using SDN principles and open interfaces. So let's look at the entities across the layers of the RAN protocol stack, focusing on the user plane. We see a G node B, a 5G base station, next generation node B, and we see a user equipment. Now, what happens here is you're basically seeing that the user is subscribing to three IP sessions. These IP sessions can be, say, Netflix or Amazon Prime, or like large file download or a YouTube stream, like any IP session. And these IP sessions can actually give you IP flows. So N IP sessions yielding IP flows, and these IP flows consist of IP packets. So firstly, inside the G node B, focusing on the user plane, there is an entity called SDAP. Okay, so there is one SDAP layer inside one G node B, but there can be multiple entities. So one user can have multiple SDAP entities based on the number of PDU sessions that he's subscribing to, based on the number of IP sessions that he's subscribing to. And the IP flows and the packets enter into these SDAP entities corresponding to the different PDU sessions, and they get mapped down to the PDCP entities. PDCP entities are responsible for maintaining, PDCP entities are mainly responsible for maintaining the, configuring the barriers. So the IP flows get mapped down to the data radio barriers, and PDCP entities are responsible for configuring the data radio barriers. And then from the PDCP entity, the PDUs are sent to the RLC entity. The RLC entity is responsible for segmentation and transmission buffering. And as we saw previously, there is one PDCP entity per radio barrier. So if there are M radio barriers for a user, there's going to be one PDCP entity per radio barrier. And similarly, there is one RLC entity per radio barrier. RLC is responsible for segmentation, transmission, buffering, etc. And data from PDUs from all these RLC entities get multiplexed onto one MAC entity. Okay, they get multiplexed onto one MAC entity. Okay, and then these are further mapped down to K cells, especially in today's scenario where there is carrier aggregation, more than one serving cell serves a user. So they get mapped onto K entities, and then these entities transmit to the user. So these are the layers of the RAN protocol stack focusing on the user plane. And similarly, you actually have the control plane where you actually have an RRC entity. There is one RRC entity which basically hosts N IP session contexts, okay, N IP session contexts, and then they are similarly mapped onto M PDCP control plane entities, which are responsible for signaling radio barriers. So previously in the user plane, you saw data radio barriers, and here it is signaling radio barriers. So there's going to be one signaling radio barrier per PDU session context, which the PDCP entities maintain and configure for the signaling radio barriers. And similarly, they get mapped, there is a one-to-one mapping with the RLC entities, and then they get multiplexed onto the MAC entity. And then for the MAC entity, transmission happens over the cells. Mostly signaling radio barrier happens over the primary cell, and that's one of the reasons why I only have dotted lines for cell 2 all the way till cell K, because even when all these cells are serving the G node B, for user plane, you'll be able to see all the cells serving the user plane traffic. But if it's a signaling radio barrier, mostly the transmission for the signaling radio barrier happens over the primary cell. And that's why I only have a straight line, a solid line for the physical cell 1, but I have dashed lines for cell 2 and cell K. Okay. Now, this is the 5G G node B architecture. So the G node B architecture has a centralized unit and one or more distributed units and one or more radio units. The centralized unit is just one unit, but it is logically split into a centralized unit control plane and one or more centralized unit user planes. Okay, and the CUCP and the CUUP are interfaced using E1, and then CUCP talks to the DU using F1 interface, and then DU talks to the RUs using the front haul interfaces. Now, the reason why you have a logical split of these nodes is to basically map the different layers of the RAN protocol stack onto these nodes. For example, RRC and PDCP control plane go to the CUCP. Since SDAP focuses on the user plane, SDAP goes to the CUUP, so is the PDCP user plane. And then you have RLC, MAC, and upper 5, which get mapped onto the DUs. And then the lower 5 for RF transmission is for the RUs. So basically, the CU operates at loop 2 granularities ranging from 10 milliseconds to the order of units of seconds to 1 second, more precisely. And while the DU is more of loop 1 or real-time granularities ranging from 1 to 10 milliseconds. And RU is, basically transmitting on a per TTI basis. So this is basically how you can envision the G node B architecture and the mapping of layers to the G node B. mapping of the layers to the logical nodes of the G node B. Now, just a quick introduction on the disaggregated RAN and virtualized RAN. So logical split BBU architecture and 5G disaggregation. So disaggregation, tries to have, a logical, makes use of the logical BBU split. The reason why you want to disaggregate the RAN is to basically have different hardware components for different logical nodes. So separate hardware components for the CU, separate hardware components for the DU, because as I said in the previous slide, CU has more of loop 2 operations, while DU has more of loop 1 operations. So you basically would need different hardware units for these, for the CU and the DU. Maybe DU requires higher processing speed and CU requires a higher state maintenance. So these are different requirements, and so you may need different hardware. And this kind of paves way for a more increased scalability, time granularity, and flexibility in implementations. Now, that's the concept of disaggregated RAN. Now, what about the virtualized RAN? So in virtualized RAN, you can actually move network functions from proprietary hardware to commercial off-the-shelf server platforms. However, note that the software implementation of the network functions like CUUP, CUCP, DU, etc., these are all proprietary. And the functions are basically virtualized functions that sit on COTS server. And those F1 and E1 interfaces that you saw are also proprietary. And the radio unit hardware is also proprietary in nature. But because of the migration from proprietary hardware to COTS platforms, there is better coordination for load management, adaptation, and performance optimization that makes use of the logical split and that makes use of COTS platforms. Plus, it is a very cost-effective deployment. When you're trying to make use of virtualization, instead of deploying, these baseband units in every cell site, you can basically migrate them to cloud platforms and make use of the cloud platforms for that. So now let's move on to the functions of the RAN protocol stack and what we exactly mean by mysteries. So let us basically start with the interaction between the RLC and MAC layer. Because when I say mysteries, there are some open issues or open algorithms or open issues basically in these aspects, which are not really covered by 3GPP standards, but they are open to implementation by the vendor. They are basically open to vendor proprietary implementation. So you basically see a G node B here. This is like a representation of a G node B, and we look at multiple buffers. We basically look at users buffers, okay, transmission buffers of the user, logical transmission buffers of user. I'm actually going to show you two users. I'm going to start with user number 1, and I'm going to show how you actually have logical transmission buffers for user number 1. Now, user number 1 has data radio bearer 1 and then data radio bearer 2, and it can also have something beyond that, but I'm just showing 2 data radio bearers for user 1. And now look at the way how the packets are basically PDUs or IP packets or PDUs are basically getting queued up or buffered in the logical buffers pertaining to the data radio bearers of user 1. So there is a logical buffer for DRB1, you see packets here. There's a logical buffer for DRB2, you're also seeing packets here. And similarly, you have another user, and you basically have, again, you have 2 logical buffers, and you're seeing queuing of IP packets pertaining to, for the flows pertaining to these data radio bearers, they are getting queued up inside the buffers, okay? And there can be more than 2 DRBs for a user, that is possible. And you can also have multiple users within that are being served by a G node B. Now, what you're seeing below is the MAC layer. Now, there is one MAC entity, but it can have multiple resource block groups, okay? Multiple resource block groups that are basically corresponding to logical channels. Okay, there are like 4 logical channels that I've showed here, can be even beyond 4, but I'm just showing 4 logical channels and resource block groups within the MAC layer, within the frequency time resources of the MAC layer that correspond to multiple logical channels. And you basically see that these, the data from these DRBs, like data from the DRB1 for user 1 as well as user 2, data from DRB1, they get scheduled onto the resource block group for LCID1. Okay, so this LCID1 is corresponding to the data radio bearers. So the PDUs in these data radio bearers basically gets scheduled onto the resource blocks for logical channel 1. Similarly, the data radio bearer 2 across users 1 and 2, the PDUs in these data radio bearers get scheduled onto resource block group for LCID2. So this is basically how multiplexing is actually done. Okay, like PDUs across DRBs, across users, across buffers get multiplexed onto the frequency time resources in this particular manner. So the natural question is, how can you partition your frequency time resources into multiple resource block groups corresponding to multiple logical channel IDs? That's an interesting question. And for that, it's basically like a vendor proprietary implementation. Okay. Now let's look at the way how packets get buffered. So you're basically seeing all these packets, and then the n+1 packet is basically going into the buffer. Now, please note that the buffering of packets is very, very critical to latency, to RAN latency for a user. Now, if there is a higher buffering of packets, which means if the packets are not getting preempted from the buffers quickly, it means that the packets are getting increasingly buffered, and this will increase the RAN latency of the user, which means this is very much contingent on how the vendor is mapping the QoS flows or IP packets to the data radio bearers. So we saw that the SDAP entity basically has the IP packets, and then there is a mapping done between the IP packets corresponding to QoS flows and the data radio bearers. Now, this mapping dictates how many packets are basically corresponding to one data radio bearer, and for one data radio bearer there is one transmission buffer, and this impacts the buffering of packets in the transmission buffer. Okay, so an interesting thing to note that sometimes in some cases the latency can be high even if the throughput is high. For example, you may experience a throughput of 100 Mbps, but you can also see the latency beyond 100 milliseconds, like RTT beyond 100 milliseconds, because even if you are at a very, very good channel condition, when the arrival rate of the packets into the buffer are greater than the transmission rate, right, you will still be experiencing buffering of the packets, which may increase the RAN latency for the user, especially when he's trying to have some critical user plane operations that are latency stringent. Okay. Now, what is the other mystery here? So basically, the way how the packets are transmitted to the user over the air. Okay. So we saw how the packets are getting queued. Now, how each and every individual packet is getting transmitted to the user. Now, a packet can basically be subject to an RLC segmentation, which means a packet can be segmented into multiple PDUs. Now, you can see that a 1500 byte packet here is getting segmented into 4 PDUs. Each PDU can be of different sizes, and they need not be transmitted in consecutive TTIs, transmission time intervals. Now, each PDU is transmitted on one transmission time interval to the user. He's basically transmitted on one time slot or transmission time interval to the user. But the transmission time intervals need not be contiguous, which means they can be spaced apart. Okay, and that's basically, so the RLC PDU sizes can vary, and the transmission time intervals can be spaced apart, and the gaps between two transmissions can also vary across PDUs. Okay, so because this is dependent on the congestion in the network and also the channel conditions of the user. If the channel conditions are poor, then only smaller PDU sizes are supported. If there is congestion, then one user cannot get continuous transmission time intervals. The transmission time intervals will only be spaced apart. And when there is congestion within that resource block group, right, within that logical channel, there is again this transmission, the segmentation and transmission that happens across multiple TTIs, which are not necessarily contiguous. This will also increase the latency for a user. Okay. Now, interesting thing is, so basically, right, how the vendor is allocating resources, resource allocation is a mystery again, because the resource allocation is also a black box. So the way how the vendor is allocating resources for the users and mapping, multiplexing the users onto resource block groups, this is also a vendor proprietary implementation and a black box. Okay, but it is critical to latency. Now the next interesting thing is carrier aggregation. Now we know what is carrier aggregation, which means a user can be served by more than one serving cell. That's a very precise understanding of carrier aggregation. Now you're basically seeing the flow of data across the layers of the RAN protocol stack here. STAP, PDCP, RLC, MAC PHY. You are basically seeing 3 users and like 4 cells in this figure. And what you're seeing is you're seeing 5 data radio barriers in different colors. One is in green, one is in magenta, yellow, blue, and red. Okay, these are 5 barriers collectively to all the 3 users that you're seeing here. Now, what happens is the green barrier is for user number 1, but the green barrier is being jointly served by cell 1, which is the primary cell, which is the solid line, cell 3 and cell 4, which are the secondary cells for user 1, which are in dashed lines. But all the 3 cells are jointly serving the data radio barrier 1. Now, if you take the user 2, okay, he is subscribing to 2 data radio barriers, one in magenta and one in yellow, but only cell 2 is serving the magenta barrier, and cell 3 is serving the yellow barrier. So the cells are not jointly serving both the barriers. One cell is serving one barrier and the other cell is serving another barrier for this user. Now, if you see user 3, he is subscribing to the red barrier as well as the blue barrier. The red barrier is jointly being served by 2 cells. Cell 4 is the primary cell for this user. Cell 3 is a secondary cell. So both cell 4 and cell 3 are jointly serving the red barrier. But both cell 4 and cell 3 are jointly serving the red barrier. But cell 2 is only serving the blue barrier for this user. So the blue barrier is only being served by cell 2. It is not being served by any other cell. So the way how the barriers are basically getting scheduled to the users across the cells, this is another vendor proprietary implementation, because this is also based on which logical channel ID is serving which barrier and which logical channel ID is serving which resource block groups. Now this is another mystery, which is again a vendor proprietary implementation. Now the other thing is, interestingly, in 5G is that you have this notion of bandwidth parts, which means a single cell itself can actually have different subcarrier spacing and OFDM symbol numerologies. Okay, so there is the same cell, but it can have different numerologies. Okay, now a single user can actually be scheduled on more than one bandwidth part. Okay, so how many PRBs, and each bandwidth part will have PRBs. Okay, so how many PRBs from each bandwidth part is being scheduled to the user? This is again a vendor proprietary implementation. This is another novelty in 5G. Okay, because of the additional dimension of bandwidth part, it makes the algorithm pretty challenging, because you have to schedule bandwidth parts to the user, and within each bandwidth part you also have to schedule which PRBs or how many PRBs are basically serving the user. Now if you see here, you see across time the user is basically getting scheduled onto 4 bandwidth parts. In the second diagram, across time the user can get scheduled over 4 bandwidth parts. The first bandwidth part has more PRBs, the second bandwidth part has less PRBs scheduled for the user, the third bandwidth part has a little more, and the fourth bandwidth part has a little shorter time but more resources. So this is again vendor proprietary implementation of resource allocation. And again, I don't want to spend too much time on this diagram, but again, this basically shows how different traffic for different users are basically multiplexed onto the same PRBs and TTI. For URLLC, for EAPP, for massive IoT, how can you basically multiplex different types of traffic across different users on the same set of frequency time resources across multiple cells and across multiple bandwidth parts. So this is again basically a black box implementation. And then finally, what you have is this is a classic dual connectivity. You know that if you see here, the user can actually serve by a split barrier, which means a single barrier can be jointly served by the NR cell as well as the LTE cell. So a single barrier is being split between the 2 radio legs, 2 legs. One is the LTE leg and the other is NR leg. Okay, that is the mode of deployment of 5G today, at least in USA. we basically have a non-standalone mode of deployment where the user is basically connected to both LTE as well as 5G, and you can have a single barrier that is split between the two legs. Now the question is, what percentage of traffic is going to flow over the NR leg, and what percentage of traffic is going to flow over the LTE leg? That's another question, because the split of traffic across the two legs is very key to optimizing KPIs. So that's basically another question. And this is again a vendor proprietary implementation, because this is also not really standardized in 3GPP. And then finally, what you have is you have this MIMO beamforming, where you basically want to map the antenna elements to antenna ports. And you know that in massive MIMO, right, which is typically in 5G, it is built on multi-user MIMO, which means in the same PRBs and in the same TTIs, the transmission can be scheduled for multiple users, because there is mapping of antenna ports to antenna elements. So you can basically try to schedule multiple users in the same PRB/TTI by leveraging multiple antennae and multiple layers. Okay, so that's basically the concept of massive MIMO. So how many users can you schedule in the same PRB/TTI? How many streams of data? What should be the beamforming weights for each user? And how can you do channel estimation? Because it is very unrealistic to expect full channel feedback from the user to the RAN all the time. So, you know, what kind of channel estimations should be done, right? Because you can't really expect the user to do a full channel state information feedback to the RAN at all times. So this is again a vendor proprietary implementation. The way how he chooses multi-user MIMO groups, beamforming weights, these are all vendor proprietary implementations again. And then finally, you have this notion of PDCP duplication, which is another interesting concept in 5G, which means the packets can actually be duplicated. This can happen in carrier aggregation scenario or in dual connectivity scenario, where the same packets basically, so it's the same PDCP entity, but the PDCP PDUs are duplicated. One copy of packet goes to one RLC entity, and the other copy of packets go to the other RLC entity. And both these entities get multiplexed onto one MAC entity, and they basically get, scheduled onto two component carriers ourselves, and then they basically serve the user. Now, in dual connectivity, what happens is there is again PDCP duplication, but one copy of PDCP PDUs go over one leg, 5G leg, and the other copy goes over the LTE leg. Again, when can you activate PDCP duplication? You don't have to have PDCP duplication throughout the duration of an entire session for the user. You can activate and deactivate dynamically. So when can you activate, when can you deactivate? Maybe when there is too many channel losses, you can basically activate PDCP PDU so that the packets don't get lost. Or if the channel condition is good, you don't have to activate. Again, this is vendor proprietary algorithms. So finally, what we have is we were able to see a lot of these mysteries, right? Like RRC, selection of primary, secondary cells, QoS to data radio bearer mapping, PDCP duplication, segmentation, resource allocation, MIMO configuration. These are all functionalities, but these are all implemented in a vendor proprietary implementation in 3GPP. There is no means of configuring these things by the operator, and there is no means of having third-party solutions from vendor systems. Okay, third-party solutions which are reflected in the vendor systems. This is how legacy systems have been implemented. Now, to address the problem, this is the final part of my presentation. To address the problem, we basically have OpenRAN, where you are not just having this RAN, but you're also basically having two additional components. They are the RIC components. One is the non-real-time RIC that is deployed inside the SMO, and there is the near real-time RIC. So non-real-time RIC is used for non-real-time optimization of the RAN, and near real-time RIC is used for near real-time optimization of the RAN using open interfaces. O1 and E2, these are new interfaces, and these are open interfaces. So basically what can be done is operators and third parties who want to optimize the RAN can deploy their solutions as extensible applications inside the RIC. Okay, and then with the open interfaces of O1 and E2, these extensible applications can control the functionality of the RAN. That's basically what you're seeing using these open interfaces. Okay. Now, again, as I said, I don't have to go through the slide because once you have open interfaces, you can actually have solutions from the operator or third parties that can optimize the RAN, which is built by the vendors. That's the purpose of OpenRAN. Now, you basically have non-real-time RIC, SMO, and the near real-time RIC. Now, the non-real-time RIC is responsible for per user or per user group or cell level or slice level declarative policy. Okay, for objective utility functions or for KPI targets or for enrichment information such as guidance. They are mostly used for setting the objective and for declarative policies. Now, the SMO is responsible for cell level configuration management, for managing the configuration parameters at the cell level, and also to configure some cell level tracing or user level tracing, etc. Most of management plane functions. And then what we have is the near real-time RIC that is responsible for controlling the layers of the RAN protocol stack on a per user basis. So looking at the cycle, right? So this is the RAN, and then you basically have the RIC components. First, data is sent from the RAN to the SMO over the O1 interface. This can be cell level data or UV level data, but this is more aggregated or averaged data throughout the entire course of the session. This is more of coarse grained data. And then you basically have models in the non-real-time RIC that work on the data, and they basically send some guidance to the SMO, some recommendations to the SMO. This is step number 2. And then SMO basically tries to configure cell level parameters in step number 3. These are all happening at non-real-time granularities. M-plane configuration management. This is more of non-real-time granularities. And then policy guidance is sent in step number 4 to the near real-time RIC. Okay, that is again policy guidance on objective optimization or enrichment information, etc. This is in step number 4. And then step number 5 is about deploying machine learning model over O1 from the non-RT RIC to from the SMO to the near real-time RIC. And the near real-time RIC can actually get E2 data, which is more per UE fine-grained data across the layers of the RAN protocol stack. The difference between 6 and 1 is that 6 is more of fine-grained data, okay, across the layers of a RAN protocol stack, generated more at the per user level, per user, per DRB, per flow level, more fine-grained, while one is more coarse-grained, more aggregated. And then you can also have like a reinforcement learning kind of algorithm that sits in the near real-time RIC, and that sends control back to the ORAN nodes. This is what you see in this particular step number 7, which is the near real-time RIC sending control back to the ORAN nodes. And then step number 8 is repetition of step number 1. While the ORAN nodes reflect these control actions, optimize the functions, and basically again stream data, that is repetition of step number 1 back to the SMO, and this cycle keeps continuing. Okay, and then the final part of the presentation, I don't want to spend too much details here, but how can you basically optimize latency or something using the RIC components is. So as I said, this is the kind of data that you can send over O1. All of these are cell level or UE level data, which are more aggregated or averaged during the entire duration of the session. More non-real-time data, ranging in the order of tens of seconds or minutes, etc. So these kind of interesting data like PRB utilization, cell-wide, user-specific session throughput, session latency, signaling conditions, these are all sent over O1. Now look at the kind of data that is sent over E2. These are more UE level data, which are measurements across the RAN protocol stack, across the PDCP, RLC, MAC, upper 5 layers. These are sent at near real-time granularities, like every tenths of milliseconds. More fine-grained data, user level data across the RAN protocol stack. This is what is sent as over E2. Now, what kind of machine learning models can be deployed here? Examples are random forest is one example, and the other example is LSTM, RNN, deep neural network. These are the kind of machine learning models that can be trained, more offline machine learning models that can be trained inside the non-real-time RIC. Because these models can actually generate you predictive KPIs, predictable KPIs. So using random forest or using LSTM or using deep neural network, you can actually predict the KPIs, like predict latency, predict throughput, And this prediction can actually be sent over the A1 interface to the near real-time brick. This is sending some predictive information or ML-based policy guidance. Okay. Now the final slide, what you'll see here is what kind of machine learning models can be used inside the near real-time brick. So the previous slide, we basically saw the machine learning models that can be used inside the non-real-time brick that can be sent over A1. Now in this slide, you can see machine learning models that can be used inside the near real-time brick. Now the near real-time brick cannot really have so much of computation or storage to do offline machine learning model training. So they basically have reinforcement learning kind of machine learning models that can be done in the near real-time brick. And based on all these environments, states, actions, and rewards, the near real-time brick can exercise control actions back to the RAN. And what can be the control actions? Like all those that we saw as mysteries, right? Like as mysteries in the first part of our presentation, like flow to DRB mapping, resource allocations, cell selection, etc. These can be the control actions that can be sent from the near real-time brick by using some reinforcement learning kind of training and by using the policy guidance or enrichment information over A1 from the non-real-time brick. So the near real-time brick implements these kind of machine learning optimization algorithms. So as a conclusion, we basically looked at the RAN functions and procedures, disaggregated RAN and virtualized RAN. We comprehensively went through the mysteries of the cellular RAN, that is vendor proprietary implementation, and the need to actually have OpenRAN solutions. What is the OpenRAN architecture, and what kind of control optimization and machine learning programmable intelligence you can deploy in the RIC using standardized interfaces. That's it from the presentation. Thank you so much.